Right, hello everybody. We would like to talk about the S in IoT stands for security, or more succinctly, the Internet of Shit. I am Andrew Martin. Apologies to those of you who frankly had enough of me already this conference. I'm at Control Plane, and I've done lots of different types of engineering. And my co-speaker today?
Yes. My name is Viktor Petersson. I am entrepreneur, geek, tinkerer. I have spent too much time troubleshooting YAML in the recent years, which is probably familiar to a lot of people here. I'm the co-founder of a company called Screenly. We do digital signage, but as became evident to me over the course of this event, nobody knows what that means. But that really just means display management. So if you need remote managed screens for dashboards, whatnot, that's what we do. So this talk, what is it really about? It's talk about IoT security, or really, how long does it take your shiny new fridge to join a criminalized network? All right, great. That's not exactly what this talk is about. But what is IoT really anyways? As my good friend Dom put it, the Internet of Things is a science project focused on creating the most complex way possible of turning on a light bulb. And it's really not far from, really. You've seen failures. And with dramatically exposed attack surface, there are a lot of devices in question here, really. Devices do become obsolete in alarming pace because little to no attention is paid to security in IoT. Security is, at best, an afterthought in IoT. We really, instead of seeing security as the design flow, security is, at best, an afterthought. We can do better, can't we? This, if you may have remembered last year, was something called VNC roulette, where somebody scanned the whole public internet and checked for open VNC sessions without authentication. This is one of the targets they found, and it is a power plant accessible over VNC without password. How could that go wrong? So, what is this talk really about? We're going to talk about the state of IoT. We're going to talk about some failures. We're going to talk about what we can do about it. We're going to talk about botnets and something that's really cool that's called the Bricker bot. So, the Internet of Shit. How bad is it, Andy?
I'm glad you asked. It is pretty fucking bad. In 2015, a pair of security researchers were able to remotely exploit the Jeep SUV. They took over the internal network, and remotely, again, they exploited the update mechanism to control the vehicle's speed, to speed it up, to slow it down, and to drive it wildly into ditches. The FDA confirmed that St. Jude Medical, a pacemaker manufacturer, allows remote access to these devices. They are vulnerable. It's possible to administer incorrect pacing or shocks to the users of these devices. The vulnerability was in the transmitter that reads the device's data and remotely shares it with physicians. Does this sound familiar? It could well be the plot of a thrilling Homeland Security-based television series. But it's not just vehicles and wearables that present this attack surface. There are also the devices around our homes that are now internet connected by default. Locks are another prime target. They can be attacked in many ways and should have an update mechanism. Plain text passwords, signal replay, man-in-the-middle attacks have all been recorded against these devices. Webcams are increasingly exposed to the internet with insecure default passwords. And I suspect this guy just saw his webcam move autonomously. I hope he took it the hell offline immediately. This kind of thing poses not only a security threat, but also a threat to our privacy. Of course, it's always hilarious to see the blue screen of death. Who knows why this device spewed? It could well be a hardware fault. So, how do we build these devices, and importantly, how do we expect them to run? We expect them to run happily, in harmony with their surroundings, the flower power internet mentality. But what actually happens at runtime? They are in the most hostile of environments, with nothing to save them but the author's resiliency mindset. Because these always-on, barely secure, hardly updated devices make prime targets. So how do we solve this problem across the internet for the whole of mankind simultaneously? Viktor.
I'm glad you asked, Andy. Well, fortunately, that is actually an easy one. Because using the blockchain, of course, we can solve this. Because the blockchain, as we know, is the answer to all our problems. So, that's the end of our talk. I hope everybody have a good day. Okay, fine, that's not quite the solution to our problems. But there's this other magic bullet that we keep hearing about. Containers. But how does that relate to IoT? Well, as it turns out, there has been a push in recent years about bringing containerized workloads into actual IoT as well. And this, of course, does not work for all types of IoT devices. It only applies to slightly more high-powered devices. But given Moore's law, we'll get there to even the most low-powered device in a not too unreasonable time frame. So, we are going to cover 3 types of infrastructure, IoT infrastructures, that all heavily leverage container technology. So what's the overarching concept in these technologies? Well, very much similar to any Kubernetes-like or CoreOS-like system. You have a core system that includes the kernel and a little more. Then you have some kind of scheduler or management tool. And then all the rest of your logic resides inside some kind of application container. So with that, let's first take a look at Resin. So Resin, their tagline is git push Resin. And that basically sums up what they try to do. And what that means is that you make your changes locally, push them to a remote Git target, and they take care of the rest. And in the next slide, I'll show you how that actually works. But one of the things that they've done, and I'm rather impressed by this, is create a new project called Balena. And Balena is a fork of Docker, or to be exact, Moby. And what they've done with that is that they've reduced the footprint of Moby by about 3.5%. And perhaps more importantly for an IoT environment, they managed to create deltas, binary deltas, for the updates. And that means an environment for IoT, when you have most devices on a cellular connection, reducing the footprint of the bandwidth by 10 to 70% makes a massive, important difference. Moreover, they also improve technologies such as interruption, which also happens a lot on mobile connection. So how does it actually work? Well, as you can see here, oh, the GIF started in the wrong way. That's not good. Anyways, it's pretty simple, really. You make your changes, you commit those changes to your repository, you push them. As you do that, remotely, Resin will fire off in their build environment a build of the Docker image. When that's done, it will be sucked down by the containers, by the devices. So it's very simple. Next, we have the newest entrant in this market, and it's still heavily in alpha. I just found out about it actually this week or last week. It's very much inspired by Kubernetes as far as management goes. So it has a very much similar CLI, as you can see. You use this, and you push it, and that's basically how you interact with your remote devices. Now, I don't really know if this is going to be the next big thing, but it's still an interesting experiment that they're doing here. Next, we have Ubuntu Core. And I would say this is probably the most heavily invested product in the IoT space right now in this realm. They, by the way, it used to be called Snappy before, and that's probably a lot of you have heard about that, but it's renamed to Core. So what it is a completely different version from the regular Ubuntu. And it has this design that I showed you in the previous slide, where it has a very, very small core, and then everything else resides in something called snaps, which is basically an abstraction or some kind of framework for an application environment. And that could be a Docker container, that could be an app arm or device, it could be anything, and Andy's going to go into that in details later on. So how does it actually work? Well, it's using something called Snapcraft. And Snapcraft is really something similar to Docker build. And you run this locally or in Ubuntu's build cloud. And when you run it, it sucks in all the dependencies, and it spits out a snap file. This snap file you then upload into their app infrastructure, which is subsequently pulled down by devices. So it's basically similar to resin, but they built their own system. They did, however, spend a lot more time on security and things that comes along with that. And with that, I'm going to hand off to Andy to do a bit of deep dive on that.
So this will be familiar to you from the CoreOS paradigm, which has been obviously RIP, moved on. But there are other distributions, Snappy's, which is now Core, it's very similar, and of course Project Atomic, which is what CoreOS will roll into. They're all based on an immutable root file system with containers for the application domain. Now, this is a different trust model to a standard operating system. Instead of trusting every package that's installed and giving system-wide access to the maintainer of that package at install time, which, using a third-party apt repo, may not actually be trustworthy at all, we treat that code as untrusted. And this means there's no access to the host's file system. There are privileged or privileged APIs, and no access to user data that is not specifically linked to that snap. There is a full kitchen sink's worth of isolation mechanisms for the runtime and its data. And for those of you that have received hundreds of marketing mails this morning, it may well be fully GDPR compliant. Then there's the trusted domain. These are for applications built from the Ubuntu archives. With all the archive integrity techniques our distribution package maintainers work so hard to ensure. These may or may not run confined, and they can access any resource or data in the user's session and have limited access to the host system, including things such as discretionary access control, kernel capabilities, and the system policies that we know and love. So, running applications with this trust model separates our concerns and allows for more granular policies to be applied on a per workload basis. And we should be familiar with this because it is, of course, an extension of the core container, Kubernetes, orchestrator mechanisms. So, now that we have these snaps, or containers, running our IoT devices, what does our security model actually look like? Can we prevent all attacks by default and move to Hawaii? Sadly not. How can containers help with these attacks? Well, a compromised control server or a man-in-the-middle attack are not container concerns. These are application or distribution level problems. However, a robust update mechanism will ensure that these attacks can be mitigated properly. And of course, containers provide a nice atomic deployment mechanism because their file system is contained in the tarball of the image. Corrupt firmware, well, there should be no access to the underlying hardware at that level for the running workload. Are the applications running as root? Well, traditionally, with IoT devices, they certainly are. Cryptographically signed updates should be used to ensure that when the devices are updated, we have a chain of trust back to the original device manufacturer. Default passwords, again, it's not necessarily a container, but an application level concern, but our robust and prompt update mechanisms ensure that we can rotate those images, and therefore the keys baked into them, passwords rather, if needs be. And finally, SSH and Telnet. There should be no remote access to these devices. They should be pulling their updates from a centralized, well-known endpoint. Hidden backdoors are a guaranteed exploitation route. And of course, physical access to a device is always game over. It should be noted that if your IoT device has dropped offline, never to return, you may have an anonymous Samaritan to thank. Mr. Brickerbot attempted to solve the problem of manufacturer-abandoned IoT devices. If you look at what this Brickerbot actually does, he is writing trash to the devices. He's blowing away the disks, deleting the network rules, setting kernel threads to 1, which is a few lower than generally is required, and rebooting the device. That probably means this bot has bricked your IoT device, unless it can be reflashed. Access to these devices to run these commands is via the same mechanisms as botnets such as Mirai, which is a brute forcing of default credentials. Should the vendors be held accountable for these failures? Well, Bruce Schneier went in front of Congress a couple of years ago to argue that indeed, yes, they should, because if not them, then who? But with many of these devices coming from overseas, this was perceived as a potential trade tariff and the prospect rejected. The UK has some ideas around this, but until we see consumer or legislation-driven action, there is no incentive for manufacturers to change their ways. GDPR mentioned 3. I'm probably the only person who's excited by this. Potentially, this is something that the very broad and loosely worded legislation may impact. But until we have some case law to base this on in the UK, at least, we really have no idea if it will have any bearing. So, we can't talk about IoT without talking about botnets. Huge botnets that have caused internet-scale outages with humongous distributed denials of service. Mirai, Japanese for the future, is a malware that brute forces network devices running Linux to join them with their botnet overlords. It primarily targets online consumer devices such as IP cameras or home routers, and has been responsible for a terabit per second DDoS attack on OVH, another attack on the security researcher Brian Krebs, which had to be mitigated at a global scale by Google's privacy and freedom of speech for journalists system, and also Dyn DNS. And when Dyn DNS went down, we saw how many sites had a single point of failure in their DNS service. So Mirai was bad because the devices were internet accessible, and therefore brute forceable. And not everything is currently publicly accessible today thanks to network address translation, hiding many devices between a single IP. And of course, this will change. We're going to see some problems with the eventual proliferation of IPv6. Why is that? Because IPv4 partially relies on NATing to protect and firewall the devices behind it. This protects them from the hostile internet and is a form of security through obscurity. IP6 will blow this out of the water by giving every device a public IP. IPv6 exposes even the devices that were safely hidden away with no internet-facing attack surface. We'll have to start doing better and soon, where soon is the eventual adoption date of IPv6. So we have to build better IoT devices, and how do we do that, Viktor?
Well, thank you, Andy. Well, it turns out that it's a rather challenging problem. Andy already mentioned that it's hard to hold vendors accountable. And if vendors are not held accountable, the only thing they're going to compete on is price. And if the price is the biggest driver, why would they care about security? So that's a big problem. But we still need to change this somehow. And there are some legislative efforts that potentially can solve this. But we need to move away from the whole paradigm of the one-time purchase relationship, where it's a one-time transaction with the vendor, and move that more towards an ongoing relationships. So maybe a legally enforced mechanism will solve this, and that will most likely drive up prices. Or we're going to start seeing more of the rise of subscription-based services, where we already see that on SaaS, of course, but even for devices and more so, because at the end of the day, it needs to come from somewhere. So the important part here is that we need to start thinking as device manufacturers and the software vendors about the whole life cycle. And the device life cycle is really key here. Traditionally, we've seen that the responsibility from the vendor ends at the sale. But we need to change that and make sure that it's actually the starting point of the relationship and not the end of the journey. So that begs the question, what is the end of the relationship there, or end of life? Is it 1 year, 5 years, 10 years? What's reasonable? We don't really, there is no practice around this really. But we need to start having this discussion because it is critical that we solve this problem over the next years. So now let's dive into some common failures that we see a lot in IoT. So the biggest problem really comes back to planning ahead. Vendors, given the nature of the tradition being transactional, do not plan for things like security, because once they ship the product, that's the end of that relationship. They need to change that model so that they budget for that. And that's going to be hard to turn that trend around. If not, we're just going to see the rise of botnets still keep growing. So we want to make sure that the relationship with the vendor is on an ongoing basis rather than a one-off. So how do we design better IoT devices? Well, it's really not that different from regular server environments. We need to do the same common sense we do on our servers. We need to not use hard-coded credentials or keys. And if we do, make sure we can rotate those remotely. We need to drop permission, as was pointed out in the previous panel. We need to have a streamlined and updated deployment flow. We need to use CI/CD, basically for IoT as well. It's not that different. And perhaps more importantly, not reinvent the wheel. So many IoT vendors keep reinventing the wheel over and over because reasons. Andy already touched on this. Signed updates is really important. Finally, we should expect that our devices, when we manufacture them, that they are exposed to the public internet, because that is the reality. If you plan for that, you're ready for it. If you expect them to be not exposed, well, you're setting yourself up to failure. So, with that, I'm going to hand over to Andy for a quick round of buzzword bingo.
Thank you very much. So, these things are shiny. Istio, Kubernetes and the virtual kubelet. How can these help the IoT? Well, Kubernetes as a control plane for the IoT makes some sense. Centralized management, but only for deployments less than 300,000 containers or 150,000 pods. And if that's not suitable, we can use Istio without Kubernetes to extend the mesh onto non-container devices and VMs. Now, this could provide some utility. It can be used a la carte, as pointed out by Craig Box earlier, and features can be cherry-picked. More GDPR, with layer 7 routing, potentially data can be tagged at the HTTP level with the region of origin and never routed outside of its particular region. This is very much untested at this stage. As we've heard, 0.8 long-term support is not yet ready for Istio, but certainly these are some of the bright futures that could be realized. Microsoft's virtual kubelet is basically a shim that allows Kubernetes to be extended with any device that complies to the kubelet API. So this could be a VM, it could be a supercomputing cluster, or, of course, it could be an IoT device. The Azure IoT Edge connector for Kubernetes already utilizes these things. Back to Viktor for the lessons learned at Screenly.
Thank you, Andy. So, without doing too much of a vendor pitch here, I'm just going to go through what we have learned in our experience of designing IoT and running IoT devices. So, Screenly, being a digital signage company, we much consider ourselves an IoT company. Just quick backstory, we run thousands and thousands of Raspberry Pis around the world, and all these are driving screens. We are, as a vendor, responsible for the life cycle of these devices, meaning updates of the software, both for the operating system level and for the application layer. We really much strive to have a set-and-forget relationship with the devices, that the customer set it up and running, and that's it. We take care of the rest. So, I'm going to go through our journey from 2013, when we first launched our product, and what we've learned so far, and hopefully you can avoid these mistakes. So when we started in 2013, none of these frameworks that we talked about earlier existed. So we were forced to roll our own framework. And it's not really something that we wanted to do, but we really had to. So we started out with Raspbian, which is the Debian version tailored for the Raspberry Pi, and we hardened that significantly. Then we needed a way to orchestrate these devices remotely. And since there were no tooling available for that, we relied on some traditional DevOps-oriented tool, which in this case, we actually used Puppet. Then we threw lots and lots of glue on top of that, which was mostly Python and Bash. And then finally, of course, we had the secret sauce, which was our software player. Now, as we started growing, we started running into a lot of pain points. And one of them was a simple thing like disk image creation. There were no tooling for creating disk images, so we actually had to do this manually, which, as you can imagine, is not great. As pointed out in the previous talk, as soon as you involve humans in a problem, it tends to get a lot more complex. It was also difficult to scale. It was difficult to run at large. It was slow. And perhaps most importantly, we had no way of doing fully transactional update on the entire system. This meant that sometimes, on rare occasions, we had devices somewhat in a limbo state, where they were partially updated, but not quite. And that is not something that you want to do. So we derived a few criteria that we wanted to do for our Screely 2 player, which we shipped earlier this year. We wanted to have all our disk commits built on CI. We'll have process isolation, so that even if somebody compromised our player somehow, we display web pages, so there is an attack vector there. Even if they do that, they have not bricked the device or owned the device. They are still confined in this container. Again, transactional update was something that was important for us. We really did not want to manage our own operating system because, you know what, building and managing an operating system is really freaking hard. And we wanted that operating to be hardened by default so that we didn't have to spend time on that. As a bonus point, we would ideally like to have some kind of cryptographically signed update so that even if you man-mill that, you cannot inject a rogue update. This is where we ended up with. We ended up with, obviously, we have our Raspberry Pi. They use Ubuntu Core, and then we have our secret source running on top of that. Now, that really solved a lot of problems for us. We were able to throw out so much of our own tooling that we had written before in favor of the native tools from Ubuntu. And as we have seen, because we worked very closely with Ubuntu for the last 3 years, building an operating system, even when you are somebody like Ubuntu with a massive set of very, very talented engineers, is really freaking difficult. So by tapping into their domain expertise, which is the operating system, we were able to throw out a lot of our tools and we replaced them with much better tooling. That also allowed us to provide much better security. By tapping into what Andy previously mentioned with the whole app system, we were able to go into much more higher level security where we drop permission on players and basically give a better experience and a much better end-to-end experience for the customer. So, with that, I'm going to hand it over to Andy for a quick recap.
Right, so we've heard the same sort of things as we apply to various different types of deployments for not only traditional systems, but for containers and also containers on IoT. There is not a lot of difference here. But as always, with the invention of a new technology or an attempted new version of a paradigm, the old lessons are left behind, and we're forced to remind people that history was there for a reason. So, IoT security has been an afterthought at best. However, there is hope in the new raft of innovative IoT platforms. Patch your devices, ideally automatically, and containers can fix lifecycle and runtime security. Thank you very much.
We have some time for questions, I think, if you want. Yeah. I'm interested.